Welcome to the fourth ISSS session on computational physics with Python, and we will be starting from where we left off today. And to be precise, we will be starting from section like homework assignment 2 in today's session 4. So let me clear the terminal so that it's better visible. Okay. So let's start. We'll starting with the first question, which is about, so okay, before I start, I would also like to ask if there are any questions or anything that anyone like to clarify before the beginning of the session, then let me know. I'll now share my screen and hopefully my screen is visible. Yep. Okay. So please feel free to interrupt and ask questions whenever you feel that there is something that you don't understand. I'll revisit and try to make any confusion clear. Okay. So the first question is about write a program to calculate and print the factorial of a number entered by the user. Write your program so that it calculates the factorial using integer variables, not floating point ones. Use your program to calculate the factorial of 200. Okay. So as usual, we'll have NumPy imported. Although we may not be using NumPy for this one, but let's have it for the sake of it. And we'll call it factorial. This will take a number, integer, and give out a number which is also an integer, right? And we can go a for loop. Say we call fact equals to 1. Now we go for a for loop for I in range 1, n plus 1, right? So this goes in the range, and they will do fact equals fact times I. And then once this is done, we'll return FACT fact. Got it? So now let's see. We are going to print the factorial of, say, 200. Right? So this is what we are going to print. That's what the question asks. So when we get to this, you see that we get a very large number because, as you know, the factorial of 200 is an enormous number, and that is exactly what we get in here. So now the second part is to use floating point numbers instead of integers. So for doing that, we have to define. So now this will be float, not an integer. And for that, we have to make fact like a floating point number. And to make it floating point number, we will be making, instead of 1, one can write it as 1.0. And when you give point, then Python knows that it's a floating point number, then it will be using floating point operations. And now if you do the same thing, you see you get infinite, right? And the reason for this is that floating point numbers use the same number of bits to represent not just integers, but represent fractional values. So therefore, using the same available space to represent fractional values makes the amount of the largest integer that can be saved, or the amount of the largest number that can be saved, very small. So what I mean by this is that with only integers, you can use all the available space or the available number of bits to store an integer number, and therefore the largest integer that you can store is pretty large. given your memory requirement that it has to be some say double or like, I mean, double by double, I mean 16 bits or something, right? However, if you are using the same 16 bits but want to store something like what to say, one calls that floating point number, then you first have to store the sign. That is also true for integers as well. But then there are numbers which you have to keep track of both. There is a towards the left and also towards the right of the decimal points. But the amount of space that you have available is still 16 digits that you can store. So, or 16 bits that you can store. So if you can store 16 bits, but now you have both integers and as well as non-integers numbers because it's a floating point numbers, then the largest number of floating point number that you can store becomes small. And this value is smaller than the value of factorial of 200. And that is why what you get is infinite. And this is what is happening in here. So I hope this is clear. Please let me know. If there is any question regarding this. Okay. So you can, for example, even search what's the largest value of integer that you can store in Python. Let's also do that. Largest integer value in Python. So you see if it is you are using the largest value, you can use something like this sys.maxint gives you the maximum integer. And as you see that there are 64 bits. Sorry if I had said 16 earlier, but it's actually 64 because it's a 64-bit operating system. Most likely these days, if you have 64 bits, then the largest integer that you can store is 2 to the power of 63 minus 1. So this value is very large. On the other hand, if you ask for the largest floating point number, largest float value in Python, and then again, let's look at stack. So if you go sys.float info, then you will see that the largest floating point number is actually something else. Anyways, so this was what I wanted to talk about in here. And now if there are any questions, then please ask. If there are no questions, then I'll proceed to the next question, and I will assume that everything is fine. But even later on, if you think there are some thing that you do not understand, please feel free to ask, or you can also post it in the chat. I'll be happy to answer. Okay, so let's move on then. Make this a bit large for everyone to see properly. Okay, so write a program that takes as input three numbers a, b, c and prints out the solutions or to the quadratic equation ax squared plus bx plus c. Use your program to compute the solutions of this. Okay. So there are, so now we are going to say def root, quad root, let's say, let's call this quad root. And all we need is a, b, and c, right? And then we can return, say let's call it discriminant is nothing but b squared minus 4 times a times c. We all know that this is the value of the discriminant, right? And so let's make it small just for the sake of it, not making it complicated. So b squared minus 4ac is the discriminant. So if you want to find out the root of this, it will be something like a root 1 equals to, so we do a minus b plus np dot square root of d. This whole thing has to be divided by twice a, 2 times a, right? And then we go to the next root, where we do this. Okay, so now this gives me two roots to the equation, and I return as an array root 1 and root 2. So I've made an error in here. This has to be root 2. Okay, so let's test it. Let's say, let's see, 5x squared. This is an example minus, let's think about something. So let's say 2x minus 3. So I'm just thinking of something which is which we can like already know an answer to, just to verify. So we can solve this quadratic equation. So it will be 2x squared. So say solve this 2x squared, then minus 4x minus 3x, so minus 5x plus 6, right? So let's try to solve this equation, and we know that the two roots are 1.5 and 2. So let's see if we get it or not. So all we are going to do is print. So a is 2. So we will do quad root. A is 2 because we know 2x squared, b is minus 5. So the form of this, as always, is a x squared plus b x plus c. And the c will be 6, right? And now if I run this, let's see what I get. So it says invalid value. So let's see, why does it say so? What was it? 2x. Did I do something wrong in here? Let's verify this. Okay, got it. This has to be 7x, right? Because this is minus 4x and there is minus 3x minus 7x. So yeah, here is it. And now I think this will work. This has given an error because the roots are imaginary in this specific case. Now let's see. Yes, so we got it. So the first root is one of the root is 2 and the other root is 1.5. So this works fine. And now let's test it with the stuff that has already been asked in the code. So let's test it with the other A, B, and C's. So here the A is 0.001, 001. B is 1000. And C is again 0.001. Right. So let's now do this. You see that we get two values in here using this formula. And let's try to see if these satisfy the equation or not. So for that, all we have to do is we are going to print A times x squared plus B times x plus C. So this is what we are going to print, and x is one of these values. So let's take this one. And let's see what we get. We get something which is close to 0, but not quite. Let's see if this is a good acceptable solution or not. And we will do the other as well. And we again get a value which is close to 0, but not exactly 0, right? So let's try to see that whether these roots make sense or not, right? So here it says that there is another way to write the roots of the quadratic equation, multiplying the top and the bottom by minus b minus plus of b square minus 4ac by 2a. You can write the solution to be this. So let's code the other way of finding root up, and we will call that quad root 1. So all these when then will be quad root 1, and we will have another method of finding this one where we have 2c divided by minus b minus plus of the discriminant. So okay, so we will have this, and the root 1 will be this, and similarly right. Okay, and then we are going to return the root. So let's test the other way around for the general case, just to see if both of these make sense or not. Both should give the same roots. Okay, I forgot renaming this. Let's clear it. And fair enough. We see that both of them, at least for the case where we were testing it with 2x squared minus 7x plus 6, we get the values that we are expecting. Okay, so now let's test it with the other value and see what we get. we'll call the other function. And you see that the values which we are getting is a bit different from the other value. And we were again going to test this then. So let's try to run this. You see here we get 0. So this is obviously a better solution compared to n minus 7, right? And now let's test the other one. Here it's really a bad solution, as you can see. We get something which is very off from 0. Okay, so now the question is then which one to choose for which root? And this is a bit of a tricky solution to it. So the idea here is that whenever your discriminant, as you can see here, if you look at the root, there are two numbers that are used in this operation in both here and here. You have a b and you have a square root of the discriminant. Now what happens is how this introduces the concept of something called floating point numbers. So for example, if you have a floating point number, this can be something like this. I'm just randomly popped in a few numbers, and how the computer treats it is that you have a some number, then point, then some numbers. And as you go down the line after the decimal point, these numbers become uncertain. And therefore, if you subtract numbers which are almost same with each other and only differs in a last few digits, then you get a number which is very small, and this number is unreliable in a sense that for a computer, as you go move down the digits in decimal points, the numbers become uncertain, and this is called floating point error. And therefore, if you subtract one number from the other which are almost comparable to one another, this would give rise to a very small number which will only have the digits at the end. And since these digits, like for example, the two numbers which are almost equal to one another can be like this, like up to these many numbers, they are the same, and then they differ in the last 5 digits. Then what will happen is that if you subtract one of the number from the other, since these last 5 digits are quite uncertain, because as you go move down in a floating point number, the numbers become uncertain in a computer. You are going to have a floating point representation where after subtracting, the numbers that we are left with become quite uncertain, and this gives rise to floating point error in your calculation. Okay, so now the question is that then the thing to look out for is that, or thing to avoid is that you should not subtract numbers which are almost equal. So now let's, keeping this in mind, let's go back and see in this case, when does something happen where things are not equal, become equal to one another. So let's look at this. So here you see we have these two functions, quad root 1 and quad root 2. Here there is, in both the cases, there is a b and there is a discriminant which is b square minus 4ac. Now imagine a case where your b square is much greater than 4ac. If b square is much greater than 4ac, then what happens is that this 4ac number is very small, and it doesn't subtract a lot of a large value from b square. And what this would mean is that this minus b and the discriminant, which is just d, and therefore if you take the square root of the discriminant, the square root of the discriminant and b become almost same as one another. So when your square root of the discriminant and b become very close to one another, then you should look in which case they are so close that when you are subtracting one from the other, you are going to have a condition where two almost equal numbers get subtracted. And then to look at, let's look at a case where b is greater than 0. So if b is greater than 0, then this is minus b, right? This is a minus b is a negative number. Then this is a positive number, because this is square root. This is always a positive number. but minus b is a negative number, right? So if b is greater than 0, this is the root 1 which is getting subtracted. So if you write b less than, b greater than 0, then this part is positive, right? And the next part, this part is negative because minus b is negative as b is greater than 0. Then this includes a subtraction. If b is less than 0, greater than 0, avoid this root, right? Because as you know that this involves subtraction of two numbers which are nearly equal, right? While in this case, you see minus b is negative, and this is also negative because square root of discriminant is always a positive number and you have minuses. So then what you have is actually a minus sign, and then you are adding two numbers, and then you are fine. So this is what you should do. Similarly, let's look at here. In this case, you see that if your b is positive, then this part is negative, and then this part is negative, then you are good to go. But again, if your b is positive, then you should avoid this root. So if b is greater than 0, then again this part is negative and this part is positive. So again you have a subtraction, and you should not subtract two equal numbers, and therefore you do something like avoid this root. Okay. So then let's once this is fixed, let's write a def quad smart root. So now this is going to make a choice, right? And the choice that it would make is that it will always avoid subtracting two equal numbers, right? So this will do something like a, b, and c. And here what I'm going to do is I'm going to call roots 1 as quad root 1 ABC. This is fine. And we go to this and write roots 2 as quad root 2 ABC, right? Now after this we are going to choose which are the ones to send. So if b is greater than 0, then we know which ones to avoid. Therefore, if b is greater than 0, then we are going to return the good ones. So the good ones will be, the first root is what we are going to avoid. So we are going to do something like roots 2, and it is the 0. So it is this one that we are going to send from roots 2, and from root 1, we are going to send this one. Since and you see these are mutually exclusive. So for root 1 is from this one, and root 2 is what we are going to send. So root 2 will be roots 1, 1, right? Else, it is simple. We just reverse the thing. We do something like roots 2, 1, and roots 1, 0. So now we are going to cover this one, where we are going to for b less than 0, we will send this. So we are going to do roots 1, 0. Let's make the order the same. And the second root will be this one. So it's roots 2, 1. Okay, so this is it. So once this is done, This is now we are going to test this. So this will not change because here now the problem doesn't occur because the b square is not much greater than 4ac in this specific case, but yet we are going to test this just for sanity check that things are working fine for a simplest trivial case. And then we are going to call smart root with the problematic case. Okay. And so let's test this. So just to not have any confusion, I'm going to clear the screen in here. And now let's run this code. And as you can see, this is working fine. And the smart root, let's see what the smart root then gives me. The smart root gives me this. It's kind of choosing best from both worlds. So let's see the first one with this value of x, I get something which is 0. And with the other value of x, I get something which is also very close to 0. So the idea here is that I choose the best of the two roots. And in the other case, as we expected, smart root doesn't improve on the previous types of roots, but it is definitely going to work better when your b square is much greater than 4ac, so that your square root of your discriminant and b becomes really comparable to one another. And then the smart root avoids subtraction of two numbers which are almost equal, which can lead to floating point errors and will give you numbers which are quite erroneous. Okay, so I hope that this is clear, and this included a part, like, although this is kind of something which is counterintuitive if you're new to computation, and this brings out the peculiarity of how a computer behaves, and something which is perfectly fine, algebraically speaking, can lead to a lot of trouble when you are trying to apply this in computation. And so these are some nuances that one might need to keep in mind when writing code for real world. And this is a classic example of such a nuance which arises while doing computation. So I hope that this is clear to you. I appreciate that this is quite tricky, and please feel free to pause me and interrupt if you have any questions before I move on to the next one. Okay, assuming that there are no questions, then let's move on to the next one, which is about calculating derivatives. So suppose we have a function f of x and we want to calculate its derivative at a point x. We can do that with a pencil and a paper if we know the mathematical form of the function, or we can do it on a computer by making use of the definition of the derivative. Excuse me. The computer, we actually can't take the limit as delta tends to 0, but we can get a reasonable approximation just by making delta very small. Write a program that defines a function f of x, returning the value x times x minus 1, and then calculates the derivatives of the function at point x equals to 1. Using the formula where delta equals to 10 to the power minus 2, calculate the true value of the same function, derivative analytically, and compare with the answer of your program gives. The two will not agree perfectly, and why not? Okay, so let's first try to find out the derivative using this method. So the function is some function f of x, and therefore let's say def deriv. So this gives you the derivative, and you find the function and you give delta. All right. So we know from this derivative. So here I will be introducing something called callable, which I'll come to later. But for now, let's see, move along, and I'll try to explain what I mean. So we'll pass a function and we'll pass delta. And what we are going to get is df dx. And df dx is nothing but func of x, right? And we also want to find out the derivative at some particular value x. So we are doing func x minus func x, and this is x plus delta. This is the definition of a derivative that we are using in here, right? And this has to be divided by delta, right? And now we are going to return in here df dx. So this is what is going to be returned. So see that Python is a nice programming language in a sense that it allows you to pass even functions as arguments to another functions. So this func is not a variable, but it is something called a callable. And a callable, a function is actually a callable. And when you have something which is callable, then you can do something like this, where you pass the function and then you call the function with some value. Okay, so this is what a callable is. Okay, so now we are going to define the function, which is x times x minus 1. So let's call a func. Let's call f is equals to now x such that x times x minus 1. So now I think this is also a nice place where I can define something called lambda. This is the shorthand for a function in Python. And this is same as writing something like def f x return x times x minus 1. So this and what I have written earlier means exactly the same. But if you have some function which is very simple and just one line, then instead of writing this in two lines with so many tabs and a return statement and things like this, you can use something called the lambda keyword in in Python, and this will allow you to write one-liner functions. Okay, and the name of the function goes in here. The name of the function is f, right? So now once we have done this, what we are going to do is find out the derivative with this function. And so that will be deriv. We'll pass f to it at x equals to 1.0. That's what I think the question is saying, yes. And the delta will be 10 to the minus 2. So 1.0 e minus 0, 2 is where I want to find the derivative of. And let's now run this. And you see I get something which is like this. And now let's look at this function and see what it is going to give me. It is supposed to give me when I want to find out the derivative of this. Okay, so let's see. It is 2x minus x, right? So it's 2x minus, x squared minus x. So this is going to give me 2x minus 1, right? So let's see. You have something like x times x minus 1, right? So this is nothing but x squared minus x, right? So now if you want to find out the derivative, right, of this, what do you do? If you just analytically, we know that if you differentiate this function, you will get x squared gives you 2x, and this gives you 1, right? And now for x equals to 1, this is 2 minus 1, so 1. So what you are supposed to get is 1, but since this is a numerical procedure and delta is not exactly 0, the limiting case is 0. So as delta becomes smaller and smaller, you are supposed to go closer and closer to the limit. Then you will get 1. But now since delta is very small but not exactly 0, and you cannot put 0 in here because then it becomes divided by 0, which is obviously not defined. It's a limit which is defined. So then what you have after this operation is something which is close to 1, right? So now we are going to test that if we continuously keep on decreasing delta, how this value or how accurate we are in getting in this derivative when we compare it with the value which is obtained analytically, right? So let's then write this df dx thing, analytical expression as well, so that it becomes easy to compare. And this is nothing but 2 times x minus 1. This is the analytic form, right? And now let's try multiple deltas in here. So we do something like a deltas, and these are starting with -4, we will go till -14 in steps of 2. So we can do something like a log space. So let's tell you what log space looks like. So you can do something like a log space. So we'll start from -2, go till minus 14, or the other way around, till -2, and this will be in steps of 4, 5, 6, 7, 8. Okay. In steps of, okay. Instead of log space, I think the better one is arrange. So from -14 to, so we'll go from -2 to -16 in steps of -2, right? And if you do this, you see, since this is -16, which is not included, so we go from -2 to -14. So this is, then we exponent this to the power of 10. So then what we are going to do is 10 dot 0 to the power of this thing, right? So this is exactly what we can do, and then we are going to find out how this value becomes, right? So for that, we are going to call for delta in deltas, and we are going to call the derivative numerical. The numerical derivative is something. So this is, and let's also store the analytic derivative, analytic one, and we will call this df dx at x, right? And we call it at 1.0. So everything is going to be calculated at 1.0, right? And the numerical derivative is going to be calculated in here. We are going to pass the function f, and we are going to pass x to it, and the delta will be equals to delta. So delta is what we are going to pass, right? And we will get the numerical deriv num, and let's call this. So for every deltas, we are going to find out the commands. We are going to find out the deriv num. So this will be np dot zeros underscore like DL TS. So for every deltas, we are going to find this, right? And so we can do something like this in enumerate. So we are going to enumerate this into deltas, and I hope enumerate was clear to you from the previous one of the previous classes, although I'm going to repeat this. So what enumerate will do is it will go through every element of deltas. So so that is -2, -4, -6, and it will assign the position to I, so that will be 0, and the value to delta, so that is -2, and then it will be 1 for I and -4 for delta, and so on. So we have deriv num, which is the ith element, is derivative. So that is what we are going to call in here. The function is the function f, and x is where I want to do it, and delta is delta. Okay, so now once we have done, we are now going to compare, right, that how well it is doing when you compare to the analytically obtained solution. Okay, so to do that, what we are going to find out is absolute error. So the absolute error is nothing but np dot absolute value of the difference between the analytic derivative analytic minus numerical divided by analytic, right? So this is the absolute value which we are going to compare with. And let's close the bracket. So this is the absolute error. And once we have done the absolute error, we can check. So a nice way to check it is plotting. So import, we will plot it, and plot the error as a function of delta. So import matplotlib dot plot as plt. And now we are going to do plt dot plot So on x-axis, we will be having deltas. On y-axis, we are going to have absolute errors. So plt dot grid. Let's have the grid for just for the sake of it, and x label is. So now here, for example, if you want to add in something called art strings, you can use art strings in matplotlib. What this allows you to do is have symbols and LaTeX formulas. So you can give dollars, and inside dollars you can leave /delta. So this gives you the Greek delta symbol, right? So similarly, you can use mathematical equations. So these are LaTeX equations, and if you are interested in that, to know more about these, like these functions or these commands, these are LaTeX commands, and if you're interested, I would highly recommend you to check what are LaTeX. So this is how it is written. These are LaTeX commands. So this is how it is. And you can Google for LaTeX commands. There is something called overleaf, where people often write LaTeX documents. And this is super useful for scientific writing. And I would highly recommend you to check it out. Okay. So, and now we are going to have epsilon as the error, right? So now let's look at it. Let's turn on plot. This was something which we were getting from last day. So let's now run this thing. And as you can see, as delta, okay, I guess what has happened in here is that we are going to have something called the log plot. So this would allow us to really look at what's happening, because the numbers are very small. When you have numbers very small or very large and they spread over a large range, then it's better to use a logarithmic grid. And this is what we are going to do. And here it is. So now we are using logarithmic grid, and as you can see that initially, with as the delta value is kind of very large, which is like around 10 to the -3, -2, And if you keep on decreasing the value of delta, the error decreases. But this goes up to a certain extent, which is around 10 to the power minus 8. And after that, the error starts to increase once again. So now the question is, what's happening? As far as the formula is concerned for limit, it says that the smaller the value of delta is, the better is your approximation for the derivative, right? Then why is it that in the computer, when we are reducing the value of delta, we are getting an improvement only up to a certain value of delta, and then what's happening is that the value is again increasing. Okay, the error is again increasing, so the error doesn't keep on diminishing, and this is again due to the goes against the expectation of what is written in the formula, and this is also has to do with the peculiarity of floating point operations in a computer. So you see that as you keep on decreasing delta, then again f of x plus delta and f of x become comparable to one another. So then what in the numerator is happening is almost same as what was happening in the previous question for the discriminant, is that f of x plus delta and f of x become very comparable to one another, and they would then only differ in the last few decimal points. So now when f of x and f of x plus delta, which are differing by only a very last few digits in its decimal representation or in its floating point representation, then you are subtracting two numbers which are nearly equal. And we already seen that when you subtract two numbers which are nearly equal, then you have loss of precision, because what's left behind are the uncertain digits which are at the end of both the numbers, right? And this is exactly what is happening when you are keep on decreasing delta. At some point, it is the floating point error, or it's a precision error, which becomes quite significant, and then again, decreasing delta makes you go pretty much off from the analytic estimate. Okay. So now the question is, let us see like why this is happening, and which obviously we have already described. I'm sorry, but what we want to find out is that why it is 10 to the minus 8 and not something else. And the answer to this is already there in the GitHub repository. So I'll just open that up because it involves a little bit of fairly simple calculations, and I'll just show that and try to explain every bit of it. But before I do so, please clarify that this part of what I was discussing regarding floating point operations is clear or not. Okay, since there are no questions, so I hope that this part is clear. So I am going to go in here, and let's see, this is work 3. Yep, here it is. So here you see that f of x plus h, you can write it as a Taylor series expansion. So if you remember, this is from like high school stuff, where you can write a Taylor series approximation of a function, and the Taylor series approximation of a function of f of x plus h is f naught. F naught is the value of the function which is evaluated at x naught. So in our specific case, x naught is 1. So f naught plus f naught prime h plus f second derivative of f naught. So this defines derivative. So a power, this is not power, but since there is a bracket, this actually indicates the derivative. So you have a second derivative by 2 factorial h to the power of 2. And then you have third derivative divided by 3 factorial and h to the power of 3. So h cube. And f naught means the derivative is evaluated at x naught, right? So then if you rearrange these equations, what you are going to find out is that f naught prime is nothing but f of x plus h, or x naught plus h. This is exactly what the formula is. So left-hand side of it, this equation is the formula which we are using. And this is an approximation of f naught prime plus sum of some numbers, right? And this part, so if you write this equation down, you will see that if you want to find out f naught prime or the derivative of f, then you not only have this expansion, but also these additional terms which goes in powers of h. But since your h is, the h here is nothing but delta, just to be clear, in our program. And since this is much, much less than 1, the higher powers you go to, this extra terms become closer and closer to 0. So the largest value of these terms comes from the smallest power, which is 2. So that is something called the leading order term. And therefore, if we write the derivative of f as just the left-hand side, then the thing which we are neglecting are all these terms, and the greatest value that we are neglecting is the first element in this summation, which is half the second derivative of f times h, right? And this is precisely what is called the truncation error. And why is it called truncation error? By truncation, one means that cutting off abruptly. And this is exactly what we are doing, is that we are cutting off the f naught prime to this just this expansion, and we are neglecting every element in the sum. So we are truncating it. So since we are truncating it at the value of h, then the leading order truncation error, because of the truncation or abruptly cutting off, is half f naught 2, which is the second derivative of f evaluated at x equals to 1 or x naught times h, right? So this is the first type of error. And then there is another type of error, which is the round-off error or precision error, which is what is happening when we are having numbers which are, comparable to each other. So you see that there is a subtraction of numbers which are very close to one another, and then gives what this does, this gives rise to what is called the round-off error. So if you want to estimate what is the value of this round-off error, then there is epsilon m. Epsilon m is the amount of round-off error or machine precision divided by h. So this is the error that the subtraction gives you, and h is h, right? So therefore, if you want to find out how much is the total error associated with the entire thing, then you will have a truncation error plus the precision error or round-off error. So if you add the two, so the first one is the truncation error is half f naught second derivative of f evaluated at x naught times h plus em by h, right? And now if you ask at what value of h or at what value of delta is this number the largest, okay? So for doing so, what you can do is just differentiate this epsilon thought with respect to h or with respect to delta and set it equals to 0, right? So that will give you the value where the value of h where your epsilon thought is largest. Epsilon thought is the smallest. The minimum error, right? So that is equals to, so this, if you do, you see that if you differentiate the first term, you lose the h, while you introduce 1 over h square with a negative sign in the second term. And now if you set it equals to 0, since there is an h square, you get a square root. And therefore, 2 times epsilon m by f naught 2, right? So now if you look at it, let's see what it is. For x equals to 1, what is the second derivative? So to get the second derivative, if you look at here, at this expression, this is the first derivative, right? So the second derivative is nothing but 2x. The second derivative is 2, because if you differentiate minus 1, it's 0, and if you differentiate this, you are left with this 2. The second derivative is 2. So this is 2 and this is 2. So both of these get cancelled out. So all you have is square root of em. So the value of h where the error is the minimum is square root of the machine precision. And for Python, the machine precision, roughly the value of machine precision is around 10 to the power of minus 16. So if your machine precision is around 10 to the power minus 16, then what you are going to have is root 100 of 10 to the minus 16, which is roughly speaking around 10 to the minus 8, right? So epsilon m for the floating point numbers and for the computers which we are having, which is 64-bit or double precision, the epsilon m is 10 to the minus 16, and therefore your precision or your error is smallest at root epsilon m, which is 10 to the minus 8. And now this explains why there is a turnover at 10 to the minus 8. And as you can see, this is because at the value of around close to 10 to the minus 8, you have the round of error, which becomes larger, while in this case, the round of error remains almost fairly constant, while the precision error keeps on increasing. And this gives rise to worsening of the estimate of the derivative. So this is the sweet spot where you have the lowest error associated with the numerical approximation of a derivative. So is this clear? If this is not clear, then please let me know. Okay, then I think I can safely move on to the next question, where let's see, okay, which is question number 4, which is about finding the root of an equation, as far as I can say. So consider the equation x equals to 1 minus e to the power of minus cx, where c is a known parameter and x is the unknown. This equation arises in a variety of situations, including the physics of contact processes, mathematical models of epidemics, and the theory of random graphs. Write a program to solve for this equation for x using relaxation method, another name for fixed point iteration method. For the case c equals to 2, calculate a solution to an accuracy of at least 10 to the minus 6, right? So let's look at what is a fixed point iteration method or a relaxation method, right? So a fixed point iteration method or relaxation method will be close to what is called the Newton-Raphson method, which we can use, and then we are going to use something called an accelerated solution. Okay, so let's get rid of these, and let's try to code the first function up. So we are going to find out the root of an equation. So the root of an equation are the values of the unknown in an equation where the equation is equals to 0. All right. So we have to find out the value of x. So this equation can be rearranged. So that then what happens is def, let's call this function func x comma c. So for some given value of x and c, we say we are going to return, let's see, 1 minus np dot exp of minus cx c times x one minus e to the power of minus cx minus x, right? So this is exactly what we are going to return. And this is equals to 0 is when we want to find out the value of x, okay? So again, you can use lambda functions for it, and I would highly recommend you to do so. Here I have not, but think about it, how you can use a lambda function to simplify this function into just one line, or contract this function into a function worth one line. Anyways, so write a program to solve this equation for x for c equals to 2 and calculate to an accuracy of at least 10 to the minus 6. Okay, so for that, let's find out something called def, and we are going to use a fixed point iteration method where a point is going to we are going to iterate, and the point is nothing but the root, and this root is going to move towards a solution where the solution is the root of value of x. Okay, so we do something called a fixed point iteration. For this, we are going to supply a function to it, and we are going to supply the value of c, right? And we need to give also the value of an initial guess x naught, right? And then we are going to have a delta, which is equals to 0.0 e minus 0.6. As far as I know, this is the value. Okay, this is the accuracy that we want. Okay, so the Newton-Raphson method tells me that to find the value of x, while, so let's do x new is equals to some value, say mp dot. Let's start with a value which is very large, right? So now, while absolute value of x new minus x old, and x old is nothing but x naught. To start with, we start with x naught. So while x new minus x old is greater than delta, we are going to keep on iterating. So this sets the accuracy. And then what we do is we do x new is equals to x old. So now we are going to find out the derivative. So Newton-Raphson method involves derivative of a function. So we are going to do func x comma c, because that's what we going to do. And when we have to do a df dx of f comma of x old comma c, and this is again old comma c, right? Now we have to define df dx, which we haven't. So let's find out what's the derivative of this, right? So we call it df dx, and the derivative of this is of 1 is 0. The derivative of exponent e to the power of minus cx is e to the power of minus cx times minus c. So this will be c times this, and e to the power of, and minus x, the derivative of minus x is minus 1, right? And there it is. So we have found out the derivative as well, right? And we have some x old, right? So this is what we have. And then but before we are changing x new, we were making x old equals to x new, because we, before changing going to the new value of new, we are going to keep the older value becomes now the new the new value becomes the old value, and then we go to the next new value. And then we will keep on iterating this one, right? And once we are above this, we are going to return x new, right? So this is the kind of thing that we want to do. But let's first plot this function and see where this function becomes close to 0, right? So for that, let's define something called x is equals to np dot linspace, say -3 to +3, 100 points, and f is func, and we want at c equals to 2, I guess, function. The first part says yes, c equals to 2. So we x and the c value is 2. And then plt dot plot. We're just going to plot this x comma f plt dot grid, just to create the grid, plt dot x label. And let's play this. And as you can see, this crosses 0 somewhere in here. So let's have something from 0 perhaps, because this part becomes very large. So let's drop this and have something starting from 0. Okay, this is better. We start from 0, and as you can see, at the value of 0, it somehow does this. So let's do something like a 0.5. Yes, so you can see there are two roots to this. One is at 0, which is close to 0. There is one root because the function crosses this horizontal line of 0 at 0 and somewhere between 0.5 and 1, right? So let's give an x naught value and see if this is we are able to kind of predict the value between 0.5 and 1 where this function is going to have a root. So I'm just commenting this out, and let's run with a fixed point iteration. We'll pass the function func. We will pass c, which is equals to 2, and the value of x naught, which is our initial guess. We can start with a guess value of 1, right? And this is going to give me the new thing. So let's print this. So it says invalid value in scalar subtract. So let's see what's happening in here. And say this, perhaps this new is not that good. So we are going to give something like a very large number, something like this. And now you see, fair enough. Now we have given the number, which is very large. Is infinite was not a good number, so it didn't work out very well. But we have given a very large number to start with, and now we have iterated it. And you see the value which we get is somewhere between 0.5 and 1, which is 0.7968. And this is roughly where you see this turnover. So I think this part is right, in the sense that now we are able to predict the value of the root of this equation for c equals 2, and this is happening pretty well in this case where we have been able to pass the function. Okay, so is this point clear, like how this is working? And this is, by the way, is called the Newton-Raphson method. So now we can also add something called number of iterations in here, which is like how many how many times the for loop was used before we have converged. Which is an indicative of how expensive the process was, right? So let's finished in iterations. It says that we have finished in this many number of iterations. Okay, so let's see. So finished in 5 iterations. So it took 5 iterations for this to complete. So the while loop went around 5 times before we have converged to the solution within the limit of accuracy that we wanted. So for example, we can test it with an accuracy of 10 to the minus 8, right? And then for that, you see, you need more iterations. You see 6 iterations, so 1 iteration more to converge to the value of 10 to the minus 8. Anyways, so let's now make the next part. It just says modify your program to calculate the solution for values of c from 0 to 3 in steps of 0.01 and make a plot of x as a function of c. So by this x means the root as a function of c. You should see a clear transition from the regime in which x equals to 0 to a regime where a regime of non-zero x. This is another example of phase transition. In physics, this is known as percolation transition, or in epidemiology as the epidemic threshold. Okay, so now what we are going to do is we are going to solve this with multiple different types of C, multiple different values of C. So to do that, it is simple. What we are going to do is we are going to do a for loop. Let's call C vals is from 0 to 3. Oh, E dot a range from 0 to 3.01 in steps of 0, 1. I think this is right. Let me just, yeah. So now once this is done, what we are going to do in here is we're going to do a for I comma c in enumerate c vals. Again, we are using enumerate. It's one of my favorite functions in Python. This makes life very easy. And we just give the value of c. And at all point, we just have 1.0 as the guess solution. Okay. So now let's print the values of x roots is equals to np dot. So for every value of c, we will get a root. So we'll have a zeros like of c vals. This is going to give you all the values of c. And instead of print, what I'm going to do is use x roots and pass I. This must be equals to this. And that's it. So once this is done, we are going to use the plot stuffs. So just copy this and we go to this and uncomment things. Okay, the things are uncommented in here. So what it asks me to plot is see from this, you should see a clear regime in which this is plot x as a function of c. So for here, this will be c vals, and this will be x roots. So x level is c and root. Right. So let's plot this. Okay. So as you can see in here, as the question says that initially for different values of c, you have a value which is close to, which is 0, because that's the root for x equals to 0. But after a certain value, it just shifts to a value, a different value, which is the solution of the transcendental equation, and it keeps on increasing. So this is exactly what is expected, and this is what we are getting. So this matches our expectation that after a threshold, there is a transition which is happening, which is abruptly changing the root to a 0 value to a non-zero value, which keeps on increasing. So it's, you can think of this as something which is changing in the system, and the system after some threshold starts to react to it, and then it catastrophically blows off. Right. So this is has to do with epidemic and things like this, but this is called the percolation transition or phase transition, which is happening in the system. So I'll not go into the nitty-gritty details of it, but all I'm saying here is that there is an abrupt transition. And then you can see here that all these calculations took 5 iterations. Some took even 6 and 7 iterations. Some even took 27 iterations. So this requires quite a few iterations for the thing to finish. Okay, so now what this asks is solve the same equation, but with an accuracy of 10 to the minus 6. So what was the previous accuracy? 10 to the minus 6 only, but this time using a fixed point iteration with acceleration. Have your program to find out the answers. Okay, so now we are going to find out. We are going to do the same thing, but we are going to use a different method which uses acceleration. So we are going to copy this in here, but use a different function which uses fixed point with acceleration, right? So these parts are the same. The iteration is different. So the iteration is xn as x old minus f of xn. This is the same, minus xn. This is new. And then this is divided by some another thing which is called g, right? A factor called g. So let's find out what, let's just define what g is. G is f of xn. So let's write func and in func we are again going to pass func and here we are going to pass x old comma c. This is g. This divided by f of xn minus xn. This is a fairly complicated formula, and this goes by some name, the method. Let me pull that out. I've forgotten about the name, but I have it in my notes. So let me see what this method is called. Stephenson's method. Yeah, so this is something called Stephenson's method, and you can also uh, later on, if you're interested, you can look it up, like how this expression comes. I'm not going into the details of it, but this gives rise to here. This is an accelerated method, and by accelerated, I mean that here you can get to the right solution or a converged solution with less number of iterations. So the lesser the number of iterations, the faster is your program going to run. Okay, so this is it, and the entire thing minus 1 is what this method is. Okay, so let's try to do this with acceleration call. There is some error which we are encountering. So let's try to see if the first part does fine or not. Just with the value of 2. Let's see. For now, I'm going to comment this out and also get this done. And let's see if this works. Yeah, this works. And now with with acceleration, this doesn't. So let's see what's happening in here. Let's see if I have written it properly or not. F of xn minus xn by g of xn. Xn minus xn by g of xn. And g is f times f of xn. F of xn minus f of xn by f of xn minus xn. Minus 1. Okay. Let's see what I have done in here. I think what I'm doing is pretty much okay. Just have to see if the signs are properly put or not. Mm. Okay. Let's start with a different value. I think what's happening is there's an exponent, and this is becoming a large number. This is giving rise to a problem. Let's start with something like a 99. It's not stopping. X new starts with X naught. Let's see. And let's have this FBI and run this. This looks fine. With acceleration is some, well, not working. Oops. It should have worked because I think we are using the same formula, but I don't know what's happening in here. So let's see. Let me copy this formula. It might be that I'm just doing a silly mistake with the formula where I have, let me see, I have already have the formula in here. It is written in a slightly more complicated manner, which I'll just going to simplify, but yeah, well, I mean, this at least will give me a formula which is better. So we have something called x old c x old c x old c, and then there's x new. Okay, there must be, yeah, this one. Okay, let's see. Here's the same thing. Okay, so it also takes a lot more iterations to finish. And let's see where I call this Stephenson's FPI. This is where I call it with a guess value of 0.5. So I'll try with a guess value of different instead of 1. I will try a guess value of 0.5 just to see. No. This is x naught plus just some arbitrary initialization. Ten. So this is just some arbitrary initialization, and again, this I think will work fine with Newton-Raphson. Somehow with acceleration, this doesn't work out that well. Or is it because I have made it 10 to the power of minus 8? No. And without acceleration, let's print the other one as well, just to have a check. So this took more number of steps. This ideally should have taken less number of steps and given you an answer which is the same. So we are having some issues with it. Xn minus of f of xn minus xn by g of xn, x new xn minus of g of xn, and g of xn is f of xn. Xn minus of f of xn by f of xn minus xn. Thing minus 1 in here. Let's do this as well, just to no, still have the same problem. So let's search for Stephenson's method and see if there is some problem with this. It is Stephenson's. Let's see. Steffen. Stephenson's method. Let's see what the Wikipedia tells us. So divided difference. Let's see what this has done. X is x minus f of x by g of x. So did we do that? Let's see. X minus f of x equals to x minus f of x by g of x. X minus of. Okay, I think we are not using the right formula. Let's see. And before that, g of x is Just looking for the Stephenson's formula. So let's see. Yes. So this is it. X old minus f of x by g of x. Now g of x is, so this is actually g of x, which is x plus f of x. Okay. I think g is you pass x plus f of x. So g of is x old plus f of x, x plus f of x, right, minus f of x by f of x. So let's see. So g of x is f of x plus f of x func of x old plus f of x old minus of x old by f of x. Okay, now let's see. Yes. Okay, this works. So I think what had happened before is that we are using this is a correction that needs to be done from my notes. I think my notes are not right in terms of this expression for Stephenson's method, and that's why we are having some problem in here. Okay, so this needs to be corrected, and now I have the right expression for Stephenson's method, and now this is working. So let's go back in here, and as you can see, since this is an accelerated method, we are iterating and going to a solution which is much quicker. So the number of iterations is less. So let's do this for 10 to the minus 8, and perhaps we'll see a much greater difference. Okay. No, I think this is the same. So just 6 and 5. So yeah, one iteration less. Okay. So now let's try to get this one FPI, right? And let's try to run this code and we are going to get a graph which is same as this. So we have got a graph, and this uses this fixed point iterations, and we see that there are some 5, 6, 7 and iterations like this. And at some places there are 10 and 20 iterations as well. So now we are going to use the other one, which is with the acceleration, just to see if the number of iterations is decreasing or not. Here we move on to this, where we surely see that the number of iterations are decreasing, all with 3 and 4s, some 5s as well. This is the previous one. Let's see. Okay. There are these 3, 4 iterations, and then later on, I think some cases things have improved with 3 and 2 iterations. Yeah, it's hard to say, but it has been, but we have been able to show this in the other part where you see that clearly the number of iterations required is a bit low. So yeah, so this is an acceleration. The technique, I I must say that this doesn't give you much of an acceleration or much of an advantage in this specific case, but the idea here is that later on, like in terms of having different other kinds of equations, the fixed point iteration with acceleration is going to perform much better. Okay, so now let's please interrupt me if you have any questions or if you have any problems that you want to clarify. Otherwise, we can move on to the next question. I think we are also pretty much out of time today because I think with 10 minutes left, I don't think we have enough time to move on to the next question. So yeah, I think I can end here if there are no questions, and then we can continue with question number 5 from the next class. So please let me know if that is okay. Okay, since there are no questions, I don't think that I'm going to continue with the question 5 today, and instead going to end the class. And day after tomorrow with the next class, we are going to start with exercise question number 5, and we'll keep on moving through the next questions of this set. And I hope that whatever we have covered has been good enough for today, and you had been able to follow it very well and there were no questions or no confusions regarding the things that had been covered. And if you think that there are something that you want to ask, or there are some stuffs that you would like to clarify, then please ask right now, or you can also post it in the chat. I am going to keep on periodically checking the chat and trying to answer to all your doubts and questions. And on that note, I thank you all for for coming to this session and for attending the lectures. And I hope this has been beneficial to you, and this prepares you for doing computation in Python and beyond as well, and gives you a basic idea of how computers work and how you can use them for in your own advantage for solving different kinds of problems. So on that note, I would stop here and stop sharing my screen, and then see you all in the next class. Bye for now.